As we continue to look at information in section 3.2, we're going to be finding real zeros, multiplicity, and writing equations of polynomials. So the first thing we're going to do is we're going to find all real zeros of this polynomial function. A real zero means you have an x-intercept, which means the y-coordinate is 0. So we're going to replace y, or f of x, with 0 and solve. And I think I'm going to trade sides. If we're going to solve for x, we're going to look for a common factor. That's what these two terms would suggest. So it looks like -2 could factor out. You could factor out +2 if you wanted to. I'm going to go ahead and take out -2, but I'm also going to take out an x squared term. When you divide out -2x squared from -2x to the 4th, it looks like I'm going to have 2x squared as a factor. Check by distributing. Yes, I do get back to what I started with. With the negative being factored out here, I'm going to have to adjust the sign and make it minus. Okay, and when I take out 2x squared from itself, I'm taking out just 1. So -1. I'm completely factored, so I'm going to set each factor equal to 0 and solve. Dividing both sides by -2, 0 divided by -2 results in 0. Extracting the roots. I don't need to go through all that work. I can clearly see that x equals 0 would give me a 0. And that makes sense. If x is 0 here and 0 here, these terms would 0 out, giving an answer of 0. Set the other factor equal to 0, add 1, divide by 2. I'm going to write the problem down again because I know the next thing for me to do is extract the roots. Square root of 1 on top is just 1. Square root of 2. Remove the absolute value. I have 2 solutions. Whatever those decimals are, those are my solutions here. So I had 3 zeros. Okay. I could have had up to 4 zeros. The highest degree, again remember the degree is the highest exponent, degree being the exponent. I could have had 4 zeros, but no more than 4 zeros. But in this case I only had 3. And actually this 0 occurs twice because the x squared equals. Okay, let's look at another example. Let's find the zeros. So I'm going to replace f of x with 0. But again, I like to put the 0 on the right hand side. So pausing and thinking about this equation we have here, it looks like we have a common factor of x. Let's go ahead and get that divided out. The result of factoring out x from all 3 terms results in this trinomial, but this isn't done. I can still factor this. If it didn't factor, I'd have to use quadratic formula or completing the square, but I believe it does factor. And notice that the coefficient on x squared is 1. So I don't have to do factor by grouping where I create 4 terms. I can actually go from a trinomial to the 2 binomials that multiply and give me that trinomial, because this has to be x and this has to be x. Factors of -2 that add to -1. Factors of -2 that add to -1 has to be -2 and +1. Set each factor equal to 0. So this factor is going to give a solution of 2. So if 2 is the 0, then x minus 2 is the factor it came from. If x plus 1 is the factor, then its solution is going to be -1. So here a little bit later we're going to be taking solutions or zeros and putting them back into the factor that they came from. So just kind of notice the structure that x equals -1 comes from a factor of x plus 1. Notice I have three solutions. The original problem was a third-degree function, so at most I could have never had more than three, but I did find three solutions. Three real solutions, that is. You could have imaginary solutions and real solutions, a combination of both, but in that last example we had a third degree with three real solutions. All right, one more of finding real zeros. So for this third degree function I could find at most three zeros. Alright, if I'm finding zeros, I've got to let y be 0. Identifying the common factors x. Thinking about how we can solve that quadratic equation. We can complete the square, you can use quadratic formula, you can try and factor, you can extract roots. I believe it does factor. I always try and do that first. A is 1. So I don't have to factor by grouping where I create 4 terms and have to put parentheses around 2 and 2. I think it factors. This would have to be x, this would have to be x. Factors a -6 that add to 1. That would be 3 and 2 with the 3 made positive. So if -3 is a solution, it came from a factor of x plus 3. And if x equals 2 is a solution, it came from a factor of x minus 2. This third degree or cubic function actually has 3 real zeros. That means these are the 3 x-intercepts on the graph of that cubic function. So I could plot 0, 0, -3, 0, and 2, 0, and those would be the x-intercepts. Alright, that's one of 3 of our objectives. Our second objective is to consider what does it mean to have multiplicity. Alright, well let's get a little bit of background about the topic of multiplicity. Alright, so what does the topic of multiplicity mean? Well, it just means multiples. That means you have repeated zeros. Just means if you were to factor and you have an exponent once factored of k greater than 1, like 2, 3, 4, 5, that if you have a higher exponent in your factor than 1, that 0 that you're going to have from this factor occurs k number of times. So of this form right here, if k is greater than 1, this yields a repeated 0 at x equals a. A just represents number. A could be 4, so x minus 4. So x equals 4 would occur k times, which matches the exponent. Looking at this in an example will probably be more clear. Okay, a little more description about repeated zeros. Because if k is even or odd, we can talk more fully about what the graph is doing at that x-intercept. So there's 2 situations, if k is even or if k is odd. If this exponent is odd, like 3, 5, 7, then the graph is going to cross or cut through the x-axis, at x equals a. If k is even, like 2, 4, 6, 8, then the graph is going to touch or bounce off the x-axis. It won't cut clean through. So if we determine we have a multiplicity situation when we're trying to find the real zeros, we can kind of think about what the graph is doing at that x equals a or that x-intercept. So let's see what this looks like in some examples. We're going to find all zeros and then determine the multiplicity of each zero. So let's just proceed in finding the zeros. Well, if I factor this, I have no multiplicity. K in this case is 1. K in this case is 1 also. K is not greater than 1 on either of the factors, so I have no multiplicity. All I can do is find the zeros, set each factor equal to 0 and solve. So the 0 x equals 5 occurs one time. And the 0 negative 5 only occurs one time as well. There's no multiplicity. I just have two x-intercepts, one at 5, 0 and one at negative 5, 0. Okay, and if you think about it, the graph is going to cut through at these x values. It's not going to just touch and bounce off. All right, let's look at an example that does have multiplicity. We're going to switch from x to t, kind of mix it up a little bit here. All right, the directions say find all zeros, got it, and then determine the multiplicity. I can't determine the multiplicity until I have it in completely factored form. So finding the zeros, proceed as we've been. I identify a common factor of t. I can factor this trinomial. I don't have to use quadratic formula or complete the square. I don't have to use factor by grouping because a is 1. It's t here, and minus 2 and minus 2. Notice how this factor repeats. It's the same factor and occurs twice. Unlike over here I had a plus and a minus. Here the binomials are exactly the same. So another way to write that would be like this. So my two factors, okay, or excuse me, my zeros, my two zeros would be t equals 0 here. And for this one right here, I only have to write it down once since it occurs twice. My zeros are 0 and 2, but it wants me to determine the multiplicity. So I'm going to come over here. T equals 0. Multiplicity of 1, we'll abbreviate. T equals 2 has a multiplicity of 2 because that factor occurred twice. Likewise, if I come over here to example 1, x equals 5 is a 0. It has a multiplicity of 1. It occurs once, and then as well this one too, multiplicity of 1. Only one factor here, not two of them. So far we've looked at zeros and multiplicity. Okay, the third objective is to find polynomial equations. So our third and final objective, I know it's getting kind of long, but I'll try and get this in the next 5 to 7 minutes. We're going to write equations of polynomials. So it's kind of like we're doing what we've been doing backwards. We're going to be given some information about the polynomial and put everything together to come up with the equation based on what was given to us. Okay, so here's what we might see. Alright, with this given information, we're supposed to take this information and write the equation of the polynomial that has this information. Notice that we have a third degree equation. That means the highest exponent will be 3, so at least that keeps us on target. We know the 0 of -2 occurs twice, and the 0 of -1 only occurs once. So the way you tackle this is you begin to build the factors that have these zeros with the appropriate exponents. So I'm ready to write the equation of this polynomial thinking about the zeros. So -2 comes from a factor of x plus 2, and it occurs twice. The 0 of -1 would come from a factor of x plus 1, and the multiplicity is 1, so it only has an exponent of 1. Basically, you're done writing the equation of the polynomial, unless you want to expand and then multiply by x plus 1. And in this example, we'll do that just for extra practice. Foiling this first, you can go out to the side and remember multiply x plus 2 times x plus 2. But the result would give this trinomial, and we yet have to multiply it by x plus 1. As you can see, this is algebraic intensive. Alright, if we're going to expand all this, I'm going to be real methodical here, and I'm going to take each of the terms of the trinomial one at a time and multiply it into these two terms. So first I'll multiply x squared by x and 1, and then 4x by x and 1, and then finally 4 times x and 1. So x squared times x, x cubed, x squared times 1, x squared. Next, 4x times x is 4x squared. 4x times 1 is 4x. Multiply 4 times both the x and the 1. Slight cleanup here. I only have one x cubed termed, but I can collect these two x squared terms. That makes 5 of them. I can collect the like linear terms, which is 8x, and then the constant comes down. So based on some given information, some zeros, multiplicity, we can put those back into factors and do all the crazy algebra to write the equation of the polynomial. Alright, our second and final example coming up. Same objective. Let's get some information down here that we can work with to write the equation of the polynomial. Alright, so we have a 0 of -4, but it occurs twice. We have a 0 of 3, it occurs twice. And the degree is 4. So the highest exponent will be 4. Let's write the equation of the polynomial, so we'll begin it with f of x equals. Let's build the factors that these zeros come from with the appropriate exponent because of the multiplicity. -4 will come from the factor of x plus 4 squared. If it was a multiplicity of 3, I'd be putting a 3 here. 0 of 3 comes from the factor of x minus 3, multiplicity of 2. Okay, I think at this point, I might take a step. I don't know if I'll take all the steps to clean this up, but I think we can see that we'd have to FOIL quantity x plus 4, FOIL quantity x minus 3, and then thinking about multiplying those two together, we might decide otherwise. But we'll at least multiply the squares. Okay, this would be x squared plus 8x plus 16. The result of foiling or boxing this would be x squared minus 6x plus 9. Alright, and as we can see, we could multiply these two trinomials together, which if we're being methodical, I would take all three of these terms multiplied by x squared. Then I'd take again the same three terms in the first trinomial, multiply it by the middle term here. Lastly, taking all three terms of the first trinomial and multiplying it by 9. That's 9 terms. I think I'll stop here. Okay, but I think you know where the direction of this problem would go if we had to do all that. But yeah, this is a good stopping point. point. So this is an equation of our polynomial with the given information. All right, so in this video we found zeros again. We determined the multiplicity of the zeros, how many times those factors occurred based on the exponent. And then we took information about the zeros and the multiplicity and we put that all back together with the degree and came up with an equation that represented that function.